Hi there, we're Group 15 and my name is Ron. Today we'll be presenting you about our experiment, which is the determinations of caffeine by using the UV spectroscopy method. So the purpose of this experiment is actually for us to detect the amount of caffeine that we can find in such a beverage that we are using in this experiment itself. And we all know that UV spectroscopy is widely used in the industry for us to detect the concentrations of anything by using the trace elements in it. And it is a relatively low cost and simple experiment, so we can actually carry it out in our lab itself, and it won't be hard for us to do it. But before you start the experiment, please do not forget your PPE. So how does the UV vis instrument works? We have actually created an animation to show you how it actually works. And video cue, 3, 2, 1. In simple terms, there's a light source, usually a hydrogen or deuterium lamp for UV light, whereas tungsten or halogen for visible light. Among the monochromator, which uses the diffraction grading to split the incoming light into the component color of different wavelength, like a prism. A beam splitter, which divides the beam of light into two equal parallel beams of light. The sample compartment, which contain both reference and sample cell. And finally, detectors, which converts the impact of photons into electric current that can be monitored by a computer.
The equipment that we are utilizing in this experiment is this UV vis instrument. And here's the two cells that are used to fill our sample. But one thing we need to be cautious of is that we must wipe the surface of our cells before we place it into a cell holder so the results will not be interfered.
The aim of this experiment is to identify a suitable wavelength scan for caffeine while performing calibration experiment using standard solutions. On the other hand, this experiment also aims to determine the concentration of a caffeine found in beverage samples and to characterize the effect of sample dilution variation on the concentration readings produced.
From the experiment of task 1, by introducing a caffeine sample with no dilution into the sample cell, we find that the wavelength correlated to the caffeine molecule is 256.6 nanometers. Now moving on to task 2, we determine our calibration curve by increasing the concentration of caffeine in steady increments of 10 ppm from 0 ppm to 40 ppm and an extreme case of 100 ppm. Here's the results of the experiment in a table. Pause the video here if you want to view it properly. Now moving on, here's the resulting graph when we plot the concentration against absorption graph. Now we can observe a fairly linear line between the ranges of 0 ppm and 40 ppm. Thus, for maximum accuracy, we should analyze the sample within this range. Finally, to task 3. Firstly, we tested the samples with no dilution. Here's our results. Pause the video here. Now, although from the results we can see a clear and distinct separation between the values of average concentration, we must be aware that the concentration exceeds 40 ppm upper limit, which, as we discussed earlier, will not give us the best and reliable results because this is not in the linear range of the curve. Moving on, we tried diluting the samples by 10 times and here is our results. Pause the video here. Now we can see that the values of average concentration does indeed lie in the range of 0 ppm and 40 ppm. Thus, we have better results. Going further, with the dilution 50 ppm, here is our results of the experiment. Pause the video here. Now, the values of the range may indeed lie between 0 ppm and 40 ppm. However, the separation between the values of average concentration now are less clear and distinct. So to conclude, I would recommend that for maximum reliable results, we follow the values in the second set of data, which is this.
According to caffeineinformer.com, we get the concentrations of caffeine in each of the source of sample used in this experiment. Where instant coffee with 57 mg, black tea with 42 mg, green tea with 25 mg, decaffeinated coffee with 5.6 mg, and pressed coffee with 120 mg. All these scales are actually based on an 8-ounce cup size of coffee. Thus, further conversion is done by us. We converted the concentration into ppm, where instant coffee with 240.93 ppm, black tea with 177.39 ppm, green tea with 105.54 ppm, decaffeinated coffee with 23.64 ppm and pressed coffee with 506.58 ppm. Based on the literature, the sequence from lowest concentrations of caffeine to highest concentrations of caffeine goes from first is decaffeinated coffee, second is green tea, third is black tea, fourth is instant coffee, and last being depressed coffee. And according to the research that we have done, we get to identify that based on the concentration we obtain from our result, where sample 1 is decaffeinated coffee as it has the lowest concentration, sample 2 will be depressed coffee as it has the highest concentration among all of them, sample 3 is green tea, sample 4 is black tea, and lastly, sample 5 is instant coffee. Throughout this experiment, we diluted the samples by 10 times and 50 times. But what is the effect of dilution? Factor variation on the readings we obtain. To explain this, let us illustrate in this way. As a solution is diluted, the absorbance of the solution is decreased. The concept of dilution relates molar concentrations and volume. If a 1 liter of a 1 molar solution is diluted to a 2 liter molar solution, the new molar concentration will be reduced by 1/2 as the volume was doubled. Beer's-Lambert law relates that the concept of concentrations and absorbance. According to this law, absorbance and concentrations are directly proportional. If you increase the original concentration, the absorbance increases, and if you dilute the solution, the absorbance will decrease in direct proportion.
From the graph, it is shown that the experiment yields R² of 0.972, which is minimal, thus confirming the accuracy of the results and the functionality of the instrument. Okay, besides using UV spectrometry, caffeine content can also be measured using thin layer chromatography, or you could call it as TLC, and iodometric bed titration analytical method. Basically, thin layer chromatography measures the solubility with different degrees of tendency to be in the same solvent. Different solutes absorb onto the solid surface in different extent as they have different degree of adsorption characteristic due to the different degrees of dissolved tendency. Moreover, different solutes will be separated on the different positions of the solid surface. And finally, retention factor of each component can be calculated by the distance of each component substance divided by the distance traveled by the solvent from the baseline. Another method will be iodometric bed titration, which the principle is that caffeine reacts with excess accurately known amount of iodine in acidic environment, forming a soluble precipitate. Then it will be removed by filtration. By using titration of sodium thiosulfate solution with starch solution as indicator, amount of the caffeine can be found and identified. From the two methods above, based on the literature research, it is known that thin layer chromatography yields more accurate results as opposed to iodometric bed titration, as it eliminates more experimental errors than iodometric bed titration method. The downside is thin layer chromatography requires more advanced technology than iodometric bed titration, which is simpler and more feasible ways.
Right, moving on. Let me emphasize first, we are not sponsored by Asus or Starbucks or maybe Canon. We are broke, so if you want to sponsor us, feel free to do that. Anyway, so how do we achieve the most efficient analysis? First off, we need to ensure that sample isolation protocols are optimized and that the samples are purified prior to measurement. But keep in mind that a UV-vis spec does not discriminate between the sample of interest and contaminants that absorb at the same wavelength. Secondly, we need to ensure that both top and bottom measurement surfaces are clean prior to loading blanks or samples, as it is important to avoid problems with subsequent readings. Performing a blank measurement on a dirty sampling surface will result in erroneous absorbance values, such as negative spectra or sample concentration being calculated as lower than the actual values. An appropriate blank is a prerequisite for accurate concentration measurements. Use the same buffer that the samples is suspended in for the blank reading and ensure that the measurement surfaces are clean prior to loading. Seeing negative spectra when running samples is a strong indicator that either the sample pedestal are dirty or a sample has been measured as a blank in error. When selecting buffers, avoid those that contain components that absorb strongly at the wavelength of interest. All spectrometers have a detectable level of background noise contributed by the environment and electronic components. The lower detection limit of an instrument can be defined as the lowest quantity of analyte that can be distinguished from background noise. A tolerance specification may be given as either a percentage value or as a concentration for a specific analyte.
Okay, to summarize this experiment, we perform the wavelength scan for caffeine and we get a value of 265.6 nanometers. Calibration graph has also been drawn to illustrate the order of the graph, linearity and the accuracy of the instrument that we use in UV-based experiment. Furthermore, dilution effect variation in the sample source to lower the concentration in order to get more reliable concentration and results. Moreover, concentration of caffeine in beverage samples have also been calculated in order to identify the sample, which is the set B with 10 times dilution for decaffeinated coffee, pressed coffee, green tea, black tea, and instant coffee, respectively. Okay.
Thank you for watching our video.
And we're gonna appreciate it if
You give us more marks.
Let us show you an animation to me. Okay. That's a blooper, okay? That's the one that we're gonna put at the end of the video, and the beep, you gotta do it.
Yeah, sure.
Alright, so wait.
Do a graph.
Each of the source of sample used in the experiment. Where instant, wait, you just
Oh,
Jesus H. Christ. Holy Jesus. What is that? What the fuck is that?
oh, that's the thing that I've yeah, okay. I'll just start over with this line, then you cut.
Okay.
An appropriate blank is a oh my god. Prerequisite.
yeah.
Prerequisite, that's the thing,
Yeah.
okay. Prerequisite. Okay. Appropriate blank is a prerequisite. Okay. An appropriate blank is a prerequisite. What is it again? Prerequisite. This is how f***ed up English is.